Okay, so we are finished up with our linear functions for right now. We will come back to those a little later, but for right now we're going to move in and start talking about exponential functions, what that looks like, what the equations look like, kind of how we work with them, and just a few basics about exponential functions. So first off, we want to start with the parent function of an exponential, and it is y is equal to a times, the basic equation for exponential functions, y equals a times b raised to the x power. So exponential functions are defined by this equation. It is y is equal to a times b multiplied or raised to the power of x. Make sure that you pay close attention to the fact that this is superscript, meaning it is up above. It is an exponent, not just multiplication. It is an exponent that b is being raised to the power of x. So when we talk about exponential functions, there's a couple important things to remember. If b is greater than 1, then the function is what we consider to be an exponential growth, and it is increasing. Just what you would think if something's growing, it's increasing. And if that b value is between 0 and 1, then the function is an exponential decay. Meaning that it is decreasing. Okay. There's another vocabulary term that you need to make sure that you know as we talk about exponential function, and it is called an asymptote. Asymptotes are a line which the graph gets close to but never touches or crosses. It is an imaginary line that we can place on our graph, and the graph will get closer and closer to it but never touch or cross. Okay, so let's kind of talk about just some characteristics. We'll classify these graphs and we'll actually graph a few of these as well. Okay, so we're going to start with y is equal to 2 raised to the x power, and the best way to graph these is by using an xy table. So I'm going to use -2, -1, 0, 1, and 2. And I'm going to plug in these x values into the equation to find out what y is. So we start with 2 raised to the power of, 2 raised to the power of -2. And that's where we're going to get that first y value. So we use our calculators, we do 2, we raise it to the -2nd power, and we find out that it is 1/4 or 0.25, and you can use that whichever way that you would like to. You can write it as fraction or as a decimal. The next one we have is y is equal to 2 raised to the -1st power. So 2 raised to the -1st power. We're just using our calculators to find that. You end up with 1/2 or 0.5. Then we have 2 raised to the 0 power, and we know that anything to the 0 power, based on the rules from exponents that we learned in 8th grade, is 1. So 0 there, the input is 0, the output is 1. Then we do 2 raised to the 1st power is going to be 2, and then finally 2 raised to the 2nd power is 4. So these are going to be our points that we're going to graph on our coordinate plane here. So first off, we start with -2 and 1/4, so we're just barely going to be above the x-axis. Then we have -1 and 1/2, so we're going to be in between those two grid lines. We have 0, 1, 1, 2, and 2, 4. And so you start to see that quintessential exponential graph start to show. And we could actually go one step further, and if you did 3 here, we would do 2 raised to the 3rd power. We would get 2 times 2, which is 4, times 2, which is 8. And we could put another point here at 3, 8. Okay, and of course we would graph this line. It's going to continue on that way, it's going to continue on this way. And here are some of the things that we notice about this graph. So first off, B. We have A, which is some number, when we look at this equation, being multiplied by a number being raised to the power. So this right here, this 2, is going to be considered our B value. A, since there's not a specific A, is understood to be 1 in this case. So going back to our b value, if b is greater than 1, and in this case 2 is greater than 1, then we know that this is going to be exponential growth. And if you look at the equation, it is, or the graph, it is increasing. Okay, then we look at our domain. That means how far to the left is this going, how far to the right, and you'll notice it has arrows on both sides, so this is going to be all real numbers, which is the case for functions. For exponential functions, they're going to have a domain of all real numbers. And then you'll notice that there is a range here where it's going to get closer and closer. This is our asymptote here, is actually going to be our x-axis. So it's going to get closer and closer to 0, but it's never going to touch it. Okay, so exponential functions do have an asymptote. And in this case, it's going to be this line right here, the x-axis. So our y values are going to be greater than 0, but they're not actually going to touch 0. They're going to be as close as they possibly can to 0, but without touching 0. So it's going to be greater than, not greater than, or equal to. It does have a y-intercept at the point 0, 1, and we see that here where it crosses the y-axis, and the asymptote here is going to be y is equal to 0. Okay, and so we would have a similar situation when we look at number 2, except for in this case you'll notice that your b value is actually less than 1, and so it's going to be a decay, and you can graph that and look through those as well. I do want to show you a couple of other examples that are a little bit more involved. So if you look at the back here, we look at number 3. So this one actually has, again, no number being multiplied by this. So in this case, a is still 1. B, our number being raised to the power of x, is 3. And then we also have this minus 1 out here. So that's going to be part of the equation that'll help us when we start to create our ordered pairs. So I'm going to create my table here, x and y. And again, I'm just going to pick some points, some random x values, and I'm just going to keep using -2, -1, 0, 1, and 2 just to kind of help me visualize. So I'm going to take these x values and plug them in. So I'll start with y is equal to 3 raised to the power of -2 minus 1. And we use our calculators to help us with this. There's no shame in that whatsoever. Those negative exponents can get a little bit tricky sometimes. It doesn't change the value, or it doesn't change the exponent, or it doesn't change the value to a negative number. What happens when you have a negative exponent, if you remember the negative exponent rule, is that it actually drops that number to a denominator rather than a numerator. That's why we're getting fractions for our answers, like we did in the past. So we're going to take a 3, we're going to raise it to the -2nd power, and then we're going to subtract 1 from that answer. And so we end up here, if I switch that back over to a fraction, with -8/9. Or I can write it as -0.8 repeating. Okay. Then I'm going to do the same thing with the -1. I'm going to do y is equal to 3 raised to the -1st power and subtract 1. So I'm going to do 3 raised to the -1st power, and I'm going to subtract 1 from that. And I end up here with a -0.6 repeating. I plug in 0, so I have 3 raised to the 0 power, which we know anything to the 0 power is 1, and then we subtract 1 from that. Y is equal to 3 raised to the 0 power minus 1, and we get 0. Okay, we're going to do that with 1 as well. So here we take y is equal to 3 raised to the 1st power and subtract 1. Well, anything raised to the 1st power is itself, so 3 minus 1 is going to give us 2. And then finally, we're going to do y is equal to 3 to the 2nd power minus 1. So 3 squared is 9. We subtract 1 and we get 8. Okay, so that's kind of how we're working through these. All right, so let's look over here and let's go ahead and graph these points. So we have -2 and almost 1 as a point, and then -1 and just below -1/2, and then we have 0, 0, and then we have 1, 2, and then we have 2, 8. Okay, and so we'll see that this is going to be our line. Okay, we have an asymptote here where it's getting closer and closer to that -1, but it's not going to touch it. So y is going to be equal to -1 for our asymptote. That's the horizontal line that will run right here. And it will get closer and closer and closer to this invisible line, but never touch it. Okay? So because this b value again is greater than 1, it is going to be growth, and you can see that it's an increasing graph. The domain is still all real numbers. The range is going to be that asymptote again. What you'll start to notice is that our range is any number greater than that asymptote. So y is going to be greater than -1. It's going to get closer and closer to almost touch it, but it's never going to be at -1. And then our y-intercept in this case was 0, 0. Now I do want to do one more example, this time with a problem that is, let's do a decreasing or a decay problem. So I'm going to skip down, and we are actually going to do number 6. So on number 6, you'll notice that here we do have a number being multiplied by another number that's being raised to the x. So in this case, our a is 5, our b is 1/2, and then we also have this -3 out here. So those values are important for us to know. Since our b is between 0 and 1, this does make this a decay question. So it is going to be decreasing this time. So just like before, we're going to do x and y graph. We're going to plug all of these in, and then we are going to plug each of these in. So 5 multiplied by 1/2 raised to the -2nd power minus 3. So this is again a great time to pull our calculators out. 5 multiplied by 1/2 raised to the -2nd power minus 3 is going to give us a value of 17. So you'll notice that this -2nd power this time flipped that back on its head and caused it to be a numerator again. So currently it was there was a denominator here, or it was a fraction, and it flips it back in the other direction. That's what that negative does. It flips our denominators and numerators rather than actually changing it from a positive to a negative number. So keep that in mind. If it was a smaller number and we're using a negative exponent, it tends to be larger when we do that, whereas if it's a larger number, it tends to get much smaller when we use that negative exponent. Alright, so we're going to try this again. This time we're going to do with a -1. So 5 multiplied by 1/2 raised to the -1st power minus 3, and we get 7. Okay, I'm going to continue this pattern where I have 5 multiplied by 1/2 raised to the 0 power minus 3. Remember that anything to the 0 power is 1. So 5 times 1 is 5, minus 3 is 2. We have 5 multiplied by 1/2 raised to the 1st power minus 3. That's going to be 2.5 minus 3, which is -0.5. And then finally 5 times 1/2 raised to the 2nd power minus 3. This is where we're going to be getting into those smaller numbers, because we had a smaller number and we're raising it to a power, which is continue to make it smaller. So we have -1.75 here. Okay, so let's go ahead and graph these points. We have -2, 17, which is going to be up off of our graph, so we're not going to plot that one. But we do have -1, 7. I'm going to put a point there. We have 0, 2. We have 1, -1/2. And we have 2, -1.75, which is almost 2. And I may want to go one more and go to 3 and just see what happens. So I'm going to do 5 multiplied by 1/2 raised to the 3rd power minus 3. And here I get a -2.375. And so that helps me to see where I'm going now. So I do 3 and -2.375, and now I can see that line a little bit better. So again, it's decay, it is decreasing because this b value is 1/2. You'll notice that my domain is again all real numbers. The range is going to be everything, and you'll notice here that doing that extra step allowed me to see that this actually does cross that -2 and gets closer to -3, but doesn't cross the -3. So my asymptote in this case is going to be -3, so my range is going to be numbers greater than that. And then of course my y-intercept, it does cross at 0, 2, at 2 on the y-axis. Okay, so that's kind of just the basics about exponential functions. Take a minute, go ahead and complete numbers 2, 4, and 5. If you have questions, you can ask me and just get some help on those if you need to, and then we'll dig a little deeper into exponentials here in a little bit.